Good afternoon, students. So now we are going to discuss a very important topic in physics, and that is potential energy of a dipole placed in a uniform electric field. What is a dipole? Suppose we have a pair of equal and opposite charges. So I have taken out this minus q and this plus q separated by a small distance, say 2a. Then it creates a dipole. So two equal and opposite charges separated by a small distance creates a dipole. Suppose this is a minus q charge, this is a plus q charge. The distance between these two charges is very small, so this makes a dipole. And what will be the dipole moment of this particular dipole? The formula for dipole moment is, it is denoted by P. So P is equal to Q into 2. So either charge into distance between the charge. Now students, this similar dipole we have placed in an electric field. We have shown the direction from the left side to the right side. You can see there is the electric field, and we have placed a dipole here. Okay, now this plus q charge, where the force will be applied. So the force will be applied in the direction of electric field, and there is no rocket science behind it. This is a plus charge, and electric field is towards positive to negative. So here is plus, here is negative. Two like charges will attract each other. Okay, two unlike charges will attract each other, so this will go towards this. So plus q will move in this direction towards the right side, and minus q will go opposite to the direction of field, so this direction. Now students, I have a dipole, and in this dipole one force is acting in this direction, another is acting in this direction. So when a pair of forces are acting equal and opposite direction in different points, then it creates a couple. So because of the couple of force, that will be a torque will be created, and due to the torque, instead of the linear motion of the dipole, okay, remember there will not be any kind of linear motion in the dipole, there will be a rotational motion in the dipole. One force is acting in this direction, another in this direction, so this way, this is getting a torque. And what is the formula for torque? We know the formula, we have studied in class 11. The formula for torque is force into perpendicular distance. So what is the force applied? If the charge is q and electric field is E, so force applied is QE. Okay, so torque is equal to force, that is QE, into perpendicular distance. Now what is the perpendicular distance? You can understand this angle we have considered theta. Say the dipole is making an angle theta with the electric field. So for, if you are not understanding this, I can resolve it in front of you. So this angle is, okay, this is 2a. This angle we have assumed theta. So this is A, this is B, this is C. This angle is assumed to be 90 degree. Okay, what is the value of sin theta? Sin theta is equal to perpendicular upon hypotenuse. Okay, so perpendicular is BC, and divided by hypotenuse is how much? 2a. So what will be the value of BC? BC will be 2a sin theta. So students, this perpendicular distance is 2a sin theta. Okay, so let us substitute the value. Torque is equal to force into perpendicular distance. So force is QE into perpendicular distance, 2a sin theta. So Q into 2a is dipole moment P, so that will be PE sin theta. So this is the torque. Now students, if we have to calculate the work done, work is how much? Work is the product of force and displacement. Here we are, which kind of force we have to take out? Because of rotational motion, we have to consider the torque. So the small work done, dW is equal to tau dot d theta. Why we have taken d theta? We are assuming because we cannot calculate for rotating it by an angle of theta. That is why we are breaking it into parts, and we are taking very small displacement, and we have considered it d theta. So for the work done, small work done, to rotate it by very small angle d theta is dW is equal to force tau d theta. Now let us substitute the value of tau. So dW is equal to, in place of tau, we can replace it by PE sin theta d theta. Now students, small work done we have calculated. Then large work done will be integration of this. Okay, so W is equal to integration dW is equal to theta 1 to theta 2 PE sin theta d theta. Now what is this theta 1 to theta 2? We have taken the lower limit. Suppose initially it is at theta 1 angle, and we are rotating to theta 2 angle. That is why we have done limit integration. So P is constant, E is also constant. Dipole moment is considered to be constant one, and electric field is uniform. So both the constant will be taken out from the integration, and when we will do the integration of sine, we will get minus cos, and limits are theta 2 and theta 1. Now let us substitute the limits. So upper limit minus lower limit. Now students, as you can see, there is negative sign outside, and when we will take it inside, then this minus will become plus and the negative sign will become positive and vice versa. Why this will held out? Because negative sign will be multiplied inside. Now this is the work done, and work done. Suppose I am doing a work against this, and this will be stored in the form of potential energy. So when the dipole will create effort, that effort is its potential energy. So this is the potential energy of a dipole when it is placed in a electric field, that is given by Pe cos theta 1 minus cos theta 2. Now students, suppose initially theta 1 is 90 degree. So we are assuming that initially the dipole was in this position. Electric field was in this direction and dipole was 90 degree to it. That is why theta 1 is considered to be 90, and say it is rotated through an angle of theta. So initially theta 1 90, theta 2 theta. Replace the values. Theta 1 90, that is 0. Theta 2 is theta. So you will get u is equal to minus E cos theta. And what is A B cos theta? AB cos theta is A dot B. So similarly, PE cos theta can be replaced by P dot E. So this is the potential energy of a dipole when it is kept in an electric field. I hope you understood. Thank you. God bless you.